So yesterday, at the end of class, we wrote down this relation for some angular momentum and energy that's carried by some forward momentum that's crossing the black hole horizon. So just in general, for any time-like forward momentum that crosses the black hole horizon, this relationship has to hold between the amount of energy it carries and the amount of angular momentum. In particular, we noted that for a Penrose process, where we arranged especially for this energy to be negative, the angular momentum also has to be negative, so we're spinning down the black hole. And then at the end of the class, I claimed that this is actually a consequence of the black hole area theorem. So that's today we're going to discuss the black hole area theorem and black hole thermodynamics in general. So I think you discussed that some in your previous class, and here we'll talk about the sort of extra parts that come in when you have rotating black holes. Okay, so the black hole area theorem is this theorem due to Hawking in 1971. And it basically just states that if you have a black hole with some event horizon, and then you look at a slice of time that goes through this event horizon and look at the area of the event horizon on that time slice at one time, and then look at it at some later time, the area has to either remain the same or increase. So, with time. And this theorem makes a few assumptions, including the null energy condition, which seems somewhat reasonable, but it also assumes cosmic censorship. Basically that we can always sort of use the Einstein equations to predict what happens as we evolve to the future, at least for observers that sit very far away from the black hole. So, ones that are at sort of future null infinity. And so, in some sense, you can think of every time we, find a place where this area condition holds as evidence for cosmic censorship. But the cosmic censorship itself is a conjecture about properties of sort of reasonable solutions to Einstein's equations. Yeah. So to see the relation between these two things, let's calculate the area of a black hole. So for a curved black hole, we just want to basically integrate over theta and phi at r equals r plus. And if we plug in what these are at r equals r plus, get something pretty simple. Just r plus squared plus a squared times sine squared theta. So the area is just 4 pi r plus squared plus a squared. And then what we want to do is write this in terms of the mass and angular momentum of the black hole. So we'll recall that r plus is just given by this expression. So using that, yeah, and here this J is the black hole angular momentum. And for now on, I'll use delta J to be some small amount of angular momentum that's being carried across the black hole horizon. Okay, so now what we want to do, now that we have this expression, well, so first of all, let's note that for a spinning black hole, obviously if you just increase the mass of the black hole, the area will increase. But if you change both the mass and the angular momentum, it's not obvious what's going to happen, right? So in particular, you might be able to decrease the mass, but also change the angular momentum in such a way that the area would still increase. So let's vary this expression for the area of the black hole with respect to mass and angular momentum. And then we'll just do a little algebra and collect the terms of delta M and delta J. And then simplify this expression right here. And that might look familiar, so we can rewrite it again in terms of r plus, the radius of the horizon. And then that's exactly this horizon frequency, the inverse of that. So okay. So we get this nice expression for how the area of the black hole varies if we change the mass and the angular momentum by a small amount. And we can see exactly that if we want this change to be greater than 0, then again we get this, we get that this quantity also has to be greater than 0 as well, if we're assuming a black hole spin that's prograde, and then get the opposite for retrograde. So again, we get this nice relationship for the change in angular momentum and in relation to a change in the mass of the black hole, which is just the same one we had before for particles crossing the black hole horizon. So any questions about that? Okay.
Oh my god.
Guess I'll be using this board. Okay, so we can also define this quantity called the irreducible mass, or MIR, in terms of the area of the black hole. So, since this doesn't decrease, this mass of the black hole shouldn't decrease as well. And we can note that if we look at a Schwarzschild black hole where the spin is 0, then this quantity is just using the relationship we have there. It is just the mass of the black hole. So for a Schwarzschild black hole, its total mass can't decrease. However, if we have an extremal black hole where A is equal to m, then we can repeat this. And get So for extremal black hole, the irreducible mass is actually noticeably smaller than the total mass of the black hole. So we can use that to define sort of the portion of the total mass of a rotating black hole that's rotational. It's just the difference between its total and the irreducible mass. And so for an extremal black hole, it's just this. And it's about 29% of the total mass of the black hole. So if you consider an astrophysical black hole, this is kind of an absurd amount of energy. For a stellar mass black hole, that'd be something like 10 to the 47 joules. So definitely if we can find some sort of astrophysical process that would tap into this energy, I can power some very energetic events. So this this black hole area theorem that you do something to a black hole and its area has to either remain the same or increase no matter what you do it might remind us of the second law of thermodynamics. And in this case, just the area of the black hole is taking the role of entropy. So actually, Hawking and Bekenstein taught us that the area of a black hole is in fact just the entropy, up to a factor of 4 over h bar. But to actually derive that factor, you need quantum mechanics. But just classically, we can sort of go through and make an identification between laws governing black holes and sort of the ordinary laws of thermodynamics. So we already have the second law. Which is that the area of a black hole has to remain the same or increase. And so there the areas playing the role of entropy. So you can ask about the other laws. So the 0th law of thermodynamics says that if you have an object in equilibrium, then its temperature is constant. So So the next question we might have is, what is the equivalent for black holes? So to define this temperature, we're again going to use this vector chi that we use a lot in class, which is the vector that's time-like up until the black hole horizon, where it becomes null and it's future pointing. It's just given by this linear combination of the axial and time killing vectors. So as I just said, it's null at the horizon. And since it's constant in particular, it's constant on the horizon, that means that if we look at the gradient of the norm on the horizon, then this should actually, since this quantity is constant on the horizon, sorry, what?
So it should be perpendicular?
Yes, exactly. So this quantity should be, this should be normal to the horizon, which means that, in fact, if we contract it with this norm to the horizon, then it'll be 0. And this means that we can actually write this gradient as equal to some function, which, as for reasons we'll see later, I'll call 2 kappa times this vector chi. And you can sort of see immediately by taking lead derivatives with respect to chi that this kappa has to be, the lead derivative of kappa with respect to chi has to be 0. Just using the fact that if you take the lead derivative of a vector with respect to itself, you get 0. So you get 0 here, and then this has to be, lead derivative of this thing has to be 0 as well from this equation. Yeah, so we can calculate, what this kappa has to be for a curved black hole. It'll just involve taking some first derivatives of the metric and evaluating them at the horizon. But I'll just write down the expression for a curved black hole, and what you get is the following. And we can also rewrite this for later convenience as the following. Okay. Yeah, so you notice, as I just noted before, kappa is actually a constant on the horizon. And in fact, kappa is what we call the surface gravity. And it's going to sort of play the role of temperature in our black hole thermodynamics correspondence. So it is indeed constant on the horizon. And in fact, you don't have to evaluate it exactly for the Kerr solution. Though I'm not going to go through the derivation here. You can actually not even assume that you're necessarily well, you can basically only assume that you have a general stationary black hole, not necessarily in vacuum, and still derive that this kappa has to be constant in the black hole horizon. So this gives us our 0th law of black hole thermodynamics. All right, so the kappa is, which we call the surface gravity, is constant on a black hole, on a stationary black hole horizon. So just to briefly remind you why we actually refer to this kappa as a surface gravity, let's specialize to the case of a Schwarzschild black hole. So in that case, if we evaluate this expression here, we just get 1 over 4m. So let's show that that's the same as what we'll call the surface gravity.
It has an interpretation of like the acceleration that you would feel if you have something attached to a cord and you're at infinity, something like that.
Yeah, exactly. Yeah. So let's briefly go through that argument. But yeah, you're exactly right. What do I erase? Yeah, so yeah, this kappa is basically, or at least in a static spacetime, like Schwarzschild, it's the acceleration of a static observer as measured by a static observer at infinity. So we're going to have to wave our hands a little bit to say exactly what we mean by that. But so let's just write down the forward velocity for a static observer in Schwarzschild. So that means it just has a time component. And then here, this factor we can identify as 1 over v, where v is the redshift. And this is basically just if you had this static observer and it emitted a photon with some frequency omega, then at infinity, that frequency would be redshifted by this amount and observed by a static observer at infinity. And we notice in particular that as we let r go to 2m, we get closer and closer to the horizon. This is going to blow up. So you have to that'll be sort of falling closer and closer to the speed of light. Okay, so now we want to calculate the acceleration of the static observer. So just plugging in the quantities for Schwarzschild, we get this, which is 0. And the only Christoffel symbol we have to worry about is this one, and this quantity, since those are the only components, is equal to -1 just by normalization. And basically the only one of these types of Christoffel symbols that's non-zero is just the radial component. So basically there's just a radial component to the acceleration and has this magnitude. And so you can see again that as we let r go to 2m, we'll get 0 in the denominator, so this will blow up. And that makes sense because basically you can't keep sort of a observer fixed at the horizon. Once it's at the horizon, it has no choice to fall but to fall into the black hole, so you have to sort of exert a infinite amount of acceleration. However, if we combine this redshift and the acceleration, we can actually get a finite quantity. So first, just the magnitude of this acceleration. Is this, and then the quantity we'll be interested in is the redshift times, and I'm going to call this A. Yeah, so multiplying those two together, we get something simple that's well behaved even at the horizon. And so we can evaluate that at the horizon. And in fact, we get this value for kappa that we wrote down over there. Yeah, and as Ramiro was saying, we can kind of think of this as we take a very long, thin string and we attach it to an object that we lower down very close to the black hole horizon and sort of see how much tension the string has to exert to keep this observer static as measured by someone at the far end of the string that's very, very far away from the black hole. And so this is all for static spacetimes. If you're in Kerr, or you're not static, you're just stationary, you don't have this simple sort of physical experiment definition of the surface gravity, but we'll still just call kappa, defined in terms of this chi vector as the surface gravity of a stationary black hole. Okay, so we've discussed the 0th law of black hole thermodynamics and the 2nd law of black hole thermodynamics. So now we want to do the 1st law of black hole thermodynamics. So we already kind of wrote down an expression for the area of the black hole, which I didn't erase. It's up there at the top. But now we can rewrite that using this quantity kappa right there. So just combine that equation with this definition of kappa. we get this expression, and we can compare that to the first law for ordinary thermodynamics. So again, this is sort of reinforcing our identification of kappa up to some normalization constant with the temperature of the black hole, the area of the black hole with its entropy. Then we can kind of think of this as doing work on the black hole. So we did 0, first, second law. So now, finally, there's the third law of thermodynamics. So there's a couple different ways to state the third law of thermodynamics. The one that's actually the most relevant for black hole thermodynamics is the statement that in any physical process, you can't achieve temperature equals to 0. And so for our case, since temperature is kappa, that means that you shouldn't be able to achieve kappa equals to 0. So if we look at our expression for kappa here, we can notice that kappa going to 0 is actually equivalent to having an extremal black hole. So this should sort of indicate, so the third law would sort of tell us that if we have a very rapidly spinning black hole, it becomes harder and harder to spin it up more and more, such that the dimensionless spin becomes closer and closer to 1. So in one of the homework problems that you'll do this week, you'll actually see sort of the difficulties that arise with actually getting things to fall into a black hole, carrying the right amount of angular momentum to spin them up as they become closer and closer to extremality. Okay, so any questions about that? Okay, so I'm going to go back to discussing how to liberate rotational energy from a rotating black hole. So we already discussed one specific case, where we had this so-called mechanical Penrose process where you had an incoming geodesic that split into two. One fell into the black hole, one carried energy away from the black hole. That, as you can imagine, that's not a terribly realistic scenario, and it'd be hard to actually arrange for it to occur in an astrophysical process. And as some of you pointed out, we're sort of, if you're in your spaceship and you're trying to inject some material to throw into the black hole you're recycling or something, you're probably going to have some other energy to, throw the things very close to the speed of light, or some explosion to break up your particle or something like that, where you're still conserving energy, but you're probably converting some energy into some less useful form of energy, like heat or something like that. But it turns out this sort of mechanical Penrose process is actually just one example of a very general type of processes. So we're going to look at Penrose processes in general, and within this class there's some other ones that are probably much more astrophysically relevant and could actually give rise to phenomena we see with our telescopes. Okay, so gonna consider a general Penrose process where you just have some type of matter without going into the details of what that specific type of matter is. So we have matter as some stress energy tensor, and we're gonna go in and we're gonna work in the test field limit, where we basically ignore the back reaction of this matter on our Kerr spacetime. So the geometry will still just be Kerr, but we're going to look at the behavior of some matter on it. So since we're still in a Kerr spacetime, we still have our time killing vector, and we can use that to define a conserved energy current. Just by contracting our stress energy tensor with this killing vector. And to see that that's conserved, just need a short calculation. So we get this one term and second term. So this first term is 0 just by conservation of stress energy tensor. And the second term is also 0 as well, and that just comes from the killing equation. So the killing equation tells us that this has to be 0, and we symmetrize indices, and then since we're contracting it with a symmetric tensor, this whole quantity has to be 0. So this current is indeed conserved. Now we can use Stokes' theorem to integrate this current on some surface. So this is Stokes' theorem. So just as if I have some n-dimensional manifold, I integrate the divergence of some quantity over it, then that's equal to just this surface integral over the boundary of the manifold, which is one-dimensional smaller, and just contracting that 4 vector with basically unit normal times some area element for this n-1 dimensional manifold. And in particular, since we just argued that this quantity here is identically 0, if we apply this to our energy current, this should be, that means that this quantity over here has to be 0 as well. So we're going to choose M to be the following section that's bounded by the black hole horizon. So using the usual convention that null surfaces are at 45 degrees angles, and then space-like are horizontal and time-like are vertical. So we have black hole horizon here. And then I want to start at some slice of constant time, t equals t initial, and then go to t equals t final. And I could cut this surface off at some finite radius, but I'm just going to let it extend to infinity, where I'll imagine that basically all the sources go to 0. So we can basically ignore contributions from r equals infinity. And so if we look at the basically normals to this, the boundary of this manifold M that I've chosen, we have the unit normal to time-like slices here. Here, instead of being future pointing, it's going to be pointing the opposite direction. And then, usually we use this vector chi that's future pointing as well and is normal to the black hole horizon. So it goes like that. But instead, we'll use a negative of that. So it'll be pointing the opposite direction. Let's try this one more time. Okay, so basically calculating this quantity, all the different contributions from these different boundary portions, we get the following. And so this quantity here is basically, so if we evaluated out what this is, just using the unit normal to our slices of constant t and plugging in our definition of J, this is actually just something like the energy density of the stress energy tensor. So we're going to call this quantity here basically the energy on our our conserved killing energy at our time t final, and this is what we're going to call the energy on our slice of t initial, and the difference between the two is just going to be given by this quantity here, which is basically negative the flux of energy, is killing energy into our black hole. So this is basically just using the fact that we have a time-like killing vector, so we have these conserved energy just for a general stress energy tensor. And we can see again that basically if we can arrange for a flux of negative energy into our black hole, that we can actually gain more energy at a later time than we had initially. And so you can also repeat this exact same argument not for energy, but for angular momentum. So we also have another conserved current. And then we just run through the same argument again. We get a similar type expression. Yeah, and so finally, I want to find a relation between these two. So So we're going to assume that our space-time obeys the null energy condition. And that just says that if we take our stress energy tensor, contract it with two null vectors, that this should be greater than or equal to 0. And we're going to use for our null vectors just this chi vector again, and evaluate it at the horizon. So if we just take this expression and integrate it over the horizon, or well, first let's just plug in our definition of chi, get this. So just using the fact that chi is constructed from the time-like and axial Killian vectors, we get these currents instead. And then if we just integrate this over the black hole horizon, we get the following. I get just the energy flux into the black hole minus the horizon frequency omega h times the flux of angular momentum into the black hole. And that this quantity has to be greater than or equal to 0. So again, we get this same condition that we need to satisfy for our black hole area to increase. So this is a very general statement. We didn't make any specific assumptions about what type of matter we're using to get this stress energy tensor. And so, a version of this story holds, for example, for electromagnetic fields, and that's thought to give rise to the so-called Blandford-Zanaik process. So this occurs, this is basically where you have a rotating black hole, and it's thought to power a jet, basically by having an accretion disk that sources strong magnetic field lines, which the black hole's rotation winds up and causes these field lines to rotate and extract energy from the rotating black hole, and therefore power a jet. And another version of the story actually holds for waves, and we'll discuss that in detail tomorrow. And this phenomenon is known as superradiance. But before we go on to discussing those, just as a side note, I want to talk about the sort of relative roles of the black hole horizon and the ergosphere and this energy extraction, Penrose process. So on the one hand, it seems like the black hole ergosphere is sort of the essential ingredient in extracting energy, right? It's what allows us to sort of have negative energy in some region, and by creating sort of negative energy states, we can also create compensating positive energy, which can exit the ergosphere and carry energy away from our rotating object. On the other hand, this example that I just worked through basically says that we only get a change in energy from one time slice to another when we have a flux of negative energy into the black hole horizon. So something people often get confused about is, can you have a Penrose process for an object that has no horizon but does have an ergo region? So it is possible to have exotic objects, very compact rotating stars, or at least, we haven't observed such objects, but at least you can construct solutions to the GR equations where you have no horizon, but you do have an ergo region. So, in this case, would you think that you can still have a Penrose type process? Yeah, so the answer turns out to be yes. So you can kind of think of like the ergosphere as sort of like a credit card. Allows you to go into debt by having this, regions where the energy density is negative. In this ergo region, and then when this negative flux of energy crosses the black hole horizon, you can think of paying off that debt by compensating the negative energy gets compensated by a decrease in the black hole's mass. But if you don't have a horizon, you can still sort of create this negative energy in the ergosphere and create some compensating positive energy that can escape the ergosphere. It's just that you don't have anywhere for this negative energy to go. It can't fall. There's no horizon to fall down. It just has to sit in the ergo region. And so, at least in this test field limit, if there's no source of dissipation, you in fact get some sort of instability. We could just have, within the ergo region, some state that has this sort of negative killing energy that just grows and grows while sending off positive energy away from the rotating object. So that's called the ergo region instability. Yeah, so I think that's about all I wanted to talk about today.